In this video, I'm presenting ScraTouch, extending the touch interaction technique using fingernails, as an additional input modality for capacitive touch surfaces. Touch surface is the primary user interface used in smartphones and touchpads. It was originally designed to detect inputs by a fingertip. Researchers have developed new input approaches, such as using touch with a different part of a hand, such as a knuckle, nail, and side of a finger. While these approaches effectively enrich the input space, they require additional sensors or hardware. More recently, similar interaction techniques using the raw data of capacitive touch sensing have been reported. However, these techniques require kernel modification to access the raw data. We introduce ScraTouch, extending touch interaction using fingernails. The basic idea is distinguishing a fingernail from a fingertip by using capacitive touch sensing. Our technique does not require kernel modifications or external hardware. In addition, it requires only tens of milliseconds for sensing and recognition. The basic ideas of hand-part-specific interactions proposed in the prior work can also be applied to interaction scenarios for ScraTouch on touchpads, smartphones, and tabletops. ScraTouch can be used for shortcut commands, such as copy and pasting data. It shows location-based shortcuts for 3D CAD operations. The user can perform conventional pointing with a finger, and execute shortcut commands with a nail touch. Assigning a different mode to a finger and nail is also possible. The user can switch between pencil mode and eraser mode, and between absolute and relative pointing modes. Our technique has a promising possibility to integrate existing touch gestures. The user can snap a window to the corresponding direction by performing a swiping action with a nail. It shows an example of integration with the mark pad technique that invokes sub-menus by starting a touch from a bezel of the touchpad. It is possible to invoke different menus for touching by finger or by nail. It shows the equivalent circuit for the finger touch on a touch surface using shunt mode sensing. The high-frequency signal applied to the transmitter electrodes flows to the receiving electrodes through the impedance network. When a finger approaches the intersection of the electrodes, part of the signal shunts to the ground. When a user touches the surface by a fingernail, the current shunts via the fingernail and the body's impedance. The fingernail has different electrical characteristics from those of the finger. As a result, the total amount of shunt current is smaller than when touched with a finger. To access the shunt current data, we used the Multitouch Support Framework, which is a private framework for macOS. The size value is correlated with the shunt current value. It shows the distribution of the shunt current value versus the elapsed time from the start of touch. Since there is a clear difference between the current values of each input, these inputs can be simply distinguished by the threshold. We used the maximum shunt current value from the start of touch to 80 milliseconds for discrimination. We determined the threshold so that the false recognition rate is the same for each input, and the equal error rate was 3%. To evaluate the usability and performance of ScraTouch, we conducted a user evaluation involving a point-to-select task. We compared 5 types of input with different conditions for pointing and target selection methods. We selected the finger-to-finger as the baseline, and we regarded the finger-to-hold as a competitor of command invocation or mode switching. We intend ScraTouch to be used for pointing and selection. For this reason, we experimented with different combinations of nail and finger touch inputs, including the switching behavior between finger touch and nail touch. We analyzed the temporal sub-movement of the tasks. The pointing times have no significant main effect or interaction. The switching times made finger to nail and nail to finger slower than the baseline, and finger to hold, nail to nail caused no significant degradation. We estimate the reason for the longer switching times owes to bending or stretching a finger to change the pitch angle to establish contact with the touch surface in finger to nail or nail to finger. Regarding the selection times and completion times, The scratch techniques were comparable to the baseline and were faster than finger to hold. We also calculated the error rate of unintended finger and nail mode switching. The mean error rates of using scratch for pointing and selection were lower than 3% of the equal error rate. The mean error rate of nail to nail was significantly lower than that of finger to nail or nail to finger. This is probably because nail to nail does not include a transition action between the nail and finger, and participants did not frequently change the pitch angle. In sum, scratch was just as fast as the baseline, and on average, 29% faster than a long press. We also confirmed that setting a simple threshold on the measured shunt current for recognition works robustly across users. Please see the paper for detailed results, including user feedback and qualitative evaluations. Thank you.